Okay, today we will discuss the topic of structure factor. Now, we have already discussed that when we strike incident radiation like X-ray on the crystal, the diffraction takes place. So today first we will talk about how to calculate the intensity of the diffraction using this structure factor equation. We are not going to derive the structure factor equation, we are only going to use the structure factor equation. Sodium chloride, as you know already we have done, it's a face-centered cubic structure with the unit cell d spacing of 5.638 angstrom and fractional coordinates for 4 sodium and 4 chlorine atoms. Now sodium chloride, as you know, is face-centered cubic. It contains 4 molecules of sodium chloride, 4 molecules of sodium chloride. And since each molecule has 2 atoms, so it will contain 8 atoms, 4 of sodium and 4 of chlorine. 4 sodium and 4 chlorine. Now, where these are situated on the unit cell, that I will tell you when I take, for example, sodium as the origin, and that origin I am taking here. Okay, so first coordinates of that origin will be 0, 0, 0. Now, all face-centered position will be occupied by the sodium. So I will say this is the face-centered, this is one atom, this is the second atom, this is the third atom, and there will be fourth atom is this one. These 4 atoms are of sodium. So you can see their coordinates 0, 0, 0, face-centered 1 by 2, 1 by 2, 0, and then 0, not along x-axis, y-axis, and z-axis 0, 1 by 2, 1 by 2, and the other one is your, this one, these are 4, 1, 2, 3, and 4. These are of sodium. And the 4 chlorines will be, if this is sodium, the next will be chlorine. 1 by 2, 0, 0. This is sodium, this will be chlorine, 0, 1 by 2, 0. This is sodium, this will be chlorine, 0, 0, 1 by 2. And one atom is at this base, body-centered position, which you can reach by taking half step along x-axis, half along y-axis, and half along z-axis. So these are the coordinates of that particular atom of chlorine. So I have written here, sodium are situated on these xy positions, xy and z positions, and chlorine are situated on these xy and z positions. Now, what are the relative intensity of the following reflections like 111, 200, and 100? This will involve the calculation, the ratio of example of the first 2, that is 111 divided by 200. Intensity of 111 divided by intensity of 200. Now, this is your X-ray diffraction pattern, which I told you I'm using X-ray, for example, emitted by copper of a particular wavelength, and I use the diffractometer, and diffractometer gives me, this is the axis of intensity and this is the axis of 2 theta. So you can see that every peak is appearing at a particular angle in this case. So theta can be determined from here. If I know 2 theta, I can find theta. So I can use this relation 2d sine theta is equal to n lambda, n in this case is 1, so I will use this lambda. And from this I can calculate d is equal to lambda divided by 2 sine theta. Lambda, I know which incident X-ray I am using. I am using copper K alpha line, which is having a wavelength of 1.54 angstrom. And for different peaks, for example, if I take this one peak, this angle is 30, so this will be around, say, 24. So half of this will be 2 theta, so half of this will be 12 degrees. So I will use the sine of 2 into sine of lambda 1.54, d value will be equal to 1.54 angstrom divided by 2 into sine of theta. This is 2 theta, so I will use theta, sine of theta, and in this case theta is 12. So I know from the table what will be the value of sine 12, so I can find what's the value of d spacing for 111 of this diffraction plate. Similarly, this is another peak which is appearing at an angle of, say, 35 degree. So I can use again d is equal to, this will be a different value, 54 divided by 2 into sine of 35 divided by 2 will be 17.5. So in this way, I can find the d spacing for the first peak, for the second peak, for the third peak, for the fourth peak, and so on, using this particular relation, which is derived from the Bragg's law. So this will be the diffraction pattern that you will get when you are using the X-ray diffractometer. Now, basically what X-rays are doing when we throw them on the material, for example, I am using this as a beam of incident X-ray, and this is a specimen. When it interacts with specimen, it emits or absorbs certain type of radiation. First thing is, some of the incident X-ray will be absorbed, and when it is absorbed, it will be converted into heat. Second thing is, since X-ray mostly are passing through the material, so absorption will be very small, and hence the heat production will also be very small. The second thing is fluorescent X-ray, which will glow due to the X-ray. We are not interested in that. The other one is the incident X-ray can emit electrons by the two processes, which can be Compton effect or photoelectric effect. So some of the incident X-ray will be used up in creating these two effects, that is Compton recoil effect and photoelectric effect. Some of the X-rays are scattered, and they are scattered with the same wavelength. If they are scattered with the same wavelength, and these scattered X-ray can be coherent from the bound charges. Bound charges mean the charges attached to the nucleus. And incoherent which can be Compton modified from loosely bound charges. This is coherent from the bound charges, this is incoherent from the loosely bound charges. And some of the X-rays are transmitted through it. So I can say these are the interaction of incident X-ray with the specimen. And you know what specimen means. Specimen means it consists of atoms and interaction of these radiation with the atoms. And you can see here, a beam of X-ray directed at a crystal interact with the electrons of the atom in the crystal. The electron oscillate under the influence of incoming X-rays and become the secondary sources of electromagnetic radiation. Now you know that if this is the incident X-ray, this is the electron, bound electron with the atom. When these radiations are falling it, this will oscillate with the same frequency as that of incident radiation. So this electron becomes the secondary source of these X-ray emission. X-ray emission secondary source will be these electrons. Because electrons are charged particle, whenever charged particle oscillating means this is accelerated motion. Whenever a charged particle is accelerated, it will emit electromagnetic radiation. Okay? So this is how we can say electron interaction with if this becomes very large, if this amplitude is very large, then we can say you can remove this electron from the atom. The secondary radiation is in all direction. This will emit radiation in all direction. The waves emitted by the electron have the same frequency as the incoming X-rays. This is having a particular frequency, and this will oscillate with the same frequency, and radiation emitted from it will have the frequency which is equal to the frequency of the incident radiation. The waves emitted by the electrons have the same frequency as incoming X-rays, and it will be, if the atoms are situated at specific positions, this can be coherent. The emission can undergo constructive or destructive interference depending upon the path difference of the emitted electromagnetic radiation. So we can say that I will get no change in the wavelength will occur, no change in the frequency will occur when this particle is emitting electromagnetic radiation in the form of X-ray or in the form of incoming electromagnetic radiation. Now, we are going to use this equation. We start with the fundamental structure factor equation. I told you we are not going to derive this relation, we are just using this relation. This is called as structure factor, which is the combination of two parts. One is called as atomic scattering factor and other is called as geometrical structure factor. Combination of these two. So we write F as structure factor is equal to sigma n into Fn. N is the number of atom, Fn is the atomic scattering factor, and this is giving me the factor at which the atoms are contributing towards the scattered X-rays. So I've written here F, atomic scattering factor, which is defined amplitude of the wave scattered by an atom divided by amplitude of the wave scattered by an electron. Atom contains so many electrons, so atomic scattering factor will be defined as what is the amplitude of the scattered wave by an atom divided by if this amplitude is for a single electron. So this ratio we call as atomic scattering factor, which is this one, this part. This complex form is used to represent the fact that diffracted wave has an amplitude and a phase. The equation is really a notational way of saying that there are two parts, a sine part, because this can be explained as sine theta plus iota, cos theta plus iota sine theta. So we write it as Fs n into Fn cos of theta 2 pi hx plus ky plus lz plus iota this factor sine of this one. Because you can write e raised to the power iota theta as cos theta plus iota sine theta. This is the same thing which we are using here in this case. In place of theta, we will write these values h into x plus k into y plus l into z in both these cases. If I want to use Fs, I can write sigma n into Fn. Now this 2 pi is 360, so I can write cos of 360 h into x plus k into y plus l into z plus iota n into Fn sigma n into Fn sine of 360 2 pi h into x plus k into y plus l into z. This is in the form of degrees and the upper one is in the form of radians. This is illustrated in the following diagram. I can use this diagram to further write it. If this radius represents the structure factor, I can divide it into two components, this one and this one. This component is the iota sine theta, sine part, and this component is cos of cosine part, this one. So amplitude is represented as the radius of the circle and phase as the angle made to a reference direction, that is horizontal, in general. If I call this as phase angle theta, because this keeps on changing, but magnitude remains the same wherever I take, because this represents the radius of the circle. In general, we calculate the cosine and the sine part separately and then combine them using Pythagoras theorem to get the final amplitude. Now, what I will do is, I will take different structures. For example, first I am taking this structure, which is a primitive cell having atoms only at the corners. And if I say primitive cell, it means it contains only one atom. We have discussed this earlier when we were discussing the crystallography of the primitive cell, because every part, every corner atom is shared with 8 such unit cells. So contribution of this atom towards this cell will be equal to 1 by 8. So since there are 8 corners, so total I can take is 8 multiplied by 1 by 8 is equal to 1. I remove all these and I only take this one. And the coordinate of this one, since it is present at the origin, x, y, z for this will be 0, 0, and 0. Okay? I will use, before going into the calculation, you must know e raised to the power ni into pi. I can write it as minus 1 raised to the power n. E raised to the power odd n iota pi is equal to minus 1, and e raised to the power even n values into iota pi, it will give you plus 1. And from here, e raised to the power n I pi, I can write e raised to the power minus n I pi.